Hello! This lesson is entitled 1D Freefall Problems 1. We recall that when an object is in freefall on Earth, it is going to be assumed to be accelerating at negative 9.81 meters per second squared, or 9.81 meters per second squared downward. Let's try a problem or two. An alarm clock is fire escape from rest at a height of 38 meters. How long is the clock in the air? Now in the upper right we have our equation toolbox. So let's use that to help us solve this problem. We're asked how long the clock is in the air. So clearly we're asked for time. This suggests that equation B would not be a good choice, which I call the no time equation, because time is not in the equation. And how can we solve for it if it's not in the equation? So let's steer away from equation B. Similarly, we want to steer away from equation A, and that's because we're given a displacement. See right here, 38 meters, and equation A doesn't have a displacement. So that's probably not going to be a good choice either. I think the best choice is going to be equation D, because again, with equation C, we need the final velocity in order to use equation C, and we don't know the final velocity. We don't know the speed at which the clock is going to hit. So I think equation D is going to be our best choice. Since the clock starts from rest, we can simplify this expression by crossing off the VI delta t term, and we want to solve this for the time. So to do that, we want to multiply both sides by 2, divide both sides by a, and take the square root of both sides to leave us with this expression. We then put the numbers in. The displacement is downward. This clock travels downward 38 meters, so that's why my displacement here is negative 38. The acceleration, since this clock will be in free fall, is negative 9.81 meters per second squared, and that means it's going to take 2.78 seconds for this clock to hit the ground. Now let's find the velocity of the clock at impact. That means we're looking for final velocity. So we can see that equation D would be a poor choice. And these are the things we know from the previous slide and from what's given. We know the acceleration, negative 9.81 meters per second squared. We know the initial velocity to be 0 meters per second. We know the displacement to be negative 38 meters. And we just found out the time to be 2.78 seconds. And what that means is we could pretty much use any of these three other equations to help us find VF. I'm going to choose equation A. The initial speed is 0, so I'm going to solve this equation for VF by multiplying both sides by delta t. The final speed then will be the acceleration, negative 9.81 meters per second squared, times the 2.78 seconds, negative 27.3 meters per second. That is 27.3 meters per second downward. Now let's find the velocity of the clock when it's halfway down. Again, we're essentially looking for a final velocity, because final is whenever we say final is. In this case, we'll say final is halfway down. So again, equation D would be a poor choice. Now what do we know about the clock halfway down? We know its acceleration because it's in free fall, negative 9.81 meters per second squared. We know its initial velocity was 0 meters per second. And we know its displacement halfway down, because all the way down is 38 meters, or negative 38 meters. So halfway down would be half of negative 38, which would be negative 19. What we don't know halfway down is the time. We can't simply take the time that it took to get to the bottom, 2.78 seconds, and cut that in half. And we can't do that because the speed of the clock is not constant as it falls. So we do not know the time, which leads us directly to equation B, which in an earlier lesson at some point I called the no time equation. When you don't know the time and you're not asked to find the time, this is a great equation to use. So let's use it. We're going to solve this for V final. The initial speed is 0, so that term cancels. We're going to put in the numbers that we know. Notice that the displacement here will be in s negative 19 meters, just as we said a minute ago. And we're going to choose the negative velocity, not the positive one, because the object is traveling downward, negative 19.3 meters per second. Final thoughts on 1D freefall problems 1. In this lesson, we began to look at one-dimensional motion for objects in freefall. That is, objects that are acted upon only by the force of gravity. Here, we have assumed that air resistance is negligible. In such a case, any object will accelerate at negative 9.81 meters per second squared, or 9.81 meters per second squared in the downward direction. This means that if an object is falling downward, it is speeding up. If traveling upward, it is slowing down. The same 1D equations we have already met apply equally well to freefall. We'll see this some more in the next lesson. Thanks for joining me.